Okay, welcome to EGR445. In today's class, we are going to talk about bevel gears. So far, we have talked about spur gears, we talked about helical gears, we talked about the gearbox design, and now we are going to talk about the gears when the axes are intersecting. What do I mean by that? A quick recap. So far, we have looked at the gears, either spur gears or helical gears, when the gear shafts are parallel. So, and the gears could be cut parallel to the shaft or they could be at an angle. If the gears are cut parallel to the shaft, they are spur gears. If the gears are cut at an angle, at the helix angle, they are helical gears. Now think about a case wherein the gears, they are in this configuration. So you have one gear and you have the other gear, which is at certain angle. They don't need to be perpendicular. They can be at angle, but the shafts would not be parallel. The shafts would be intersecting. And then the angle of intersection could be anywhere between 10 degrees to 90 degrees. So these are called bevel gears. And a classic application of bevel gear is, imagine if you have a rear drive vehicle. So say you have a truck, and usually the trucks are rear wheel drives. So imagine you have the truck. Have you seen that in the trucks, what you have is you have something called as the prop shaft. So this shaft is rotating. You have the engine up front, but the drivetrain is in the back. So this prop shaft, there is something called as the universal joint. And universal joint, just to give you an idea, is sort of a double knuckle joint. So wherein what you have is you allow articulation at the input side, you have articulation at the output side. So if you look at the design of universal joint, the principles that you used to design a knuckle joint are applicable. So think about designing of universal joint is like you are designing two knuckle joints. The only additional steps is knuckle joint is not expected to be, it's not expected to perform operation under fatigue loading or continuous operation. On the other hand, universal joint is expected to withstand dynamic load. So you would have, just like gear trains, you will have to look at for the dynamic load and the wear load, but the concept for design of universal joint is similar to the design principles that we have been studying so far. Here, what you have is you have something called as, I don't know, if you talk to an automotive mechanic, they call this a pumpkin. This is the differential housing in which this gear is located. So if you look at, they call this a pumpkin. So you have the prop shaft, and that is connected to axle. And usually there will be two gears, something like this. So the axle on the left and the axle on the right, and you have a prop shaft that is rotating both these gears. Now, if you have identical bevel gears, so if you have identical bevel gears, they are called meter gears. And they are used in lots and lots of application, because please understand, not all the time the axes would be parallel. Many a times axes would be intersecting. But please understand, even though the axes are intersecting, they are in the same plane. They are not offsetted. Some variations that you can see in the bevel gears are, rather than cutting the gears straight, you could have gears which are cut sort of like a helical fashion. So you can see different variations in the bevel gears, but the principle or the design steps are the same. Now at this time, before I give you the outline for the design steps, I want to ask students the question, how would we design a bevel gear? Yeah, go ahead. Just a helical gear or a spur gear at angle? So what you do is, again, the same concept. Take the bevel gear, convert that into equivalent spur gear, and follow the same process. First, use WS, find the module, then find out the dynamic load, then find out the static load. Static load or static strength should be greater than the dynamic load or dynamic strength. And then you would check for the wear load, and wear load should be greater than the dynamic load. And the last step is going to be the shaft design. The only difference here is those equations that we looked at, like the Buckingham pi equation for the dynamic load, even the equation for the wear load, those equations would vary. But these 4 steps are universal steps for gear design. As a matter of fact, you won't believe that these 4 steps, coming up with a basic strength based calculation, then coming up with a dynamic load, finding the static load, finding the wear load, and then design some type of a transmission system. These steps are very common when you design the components that are subjected to dynamic loading, or they are power transmission components. For an example, similar steps are used in cam design. Similar steps are used in designing of a hypocycloid gear train. Similar steps are used when you design a planetary gear set. And any power transmission system would usually involve these steps. And at the end, what you do is, once you have designed the machine element, then you want to advance or relax your assumptions and do some advanced calculations like finite element or computational fluid dynamics, some type of calculations to make sure that the design that you have is safe. So what I'm going to do is, I'm going to start with the nomenclature for the bevel gear. So what are the principal elements of the bevel gear design? So bevel gear looks something like this. So there is a driving gear, then there is a driven gear, and there are variations in the bevel gear. I'm just going to show you one possible configuration. So this angle, it's called as the semicone angle. So I'm gonna call this as a gear and this as a pinion, with the assumption that pinion is smaller than gear, and I'm gonna call this as theta G, and I'm gonna call this as theta P. Now please understand, this distance is nothing but the pitch circle diameter of the gear. So I'm going to call this dg. Similarly, this is dp. So the important equation here is sine theta g is equal to rg divided by L, and this distance L is this distance. This distance is L. Similarly, sine theta P is Rp divided by L. And this is nothing but a simple right angle triangle or Pythagorean theorem if you want to use, that can be used to find out the relationship between the different sides of the triangle. And this L is called as the cone distance. So just like spur gear or helical gear, there are some standard dimensions. And now you know, can someone tell me what is the most important dimension in gear? What is the most important dimension in gear? Online students? Module, because everything else is associated with module. So I'm gonna give you something like speed of pinion divided by the speed of gear. Please note, pinion is going to rotate at higher RPM than gear. So speed of the pinion divided by speed of the gear is typically equal to or greater than 1. This is called as the velocity ratio is equal to dp divided by dg is equal to tg divided by tp, where dp is diameter of pinion and dg is diameter of gear. tg is number of teeth on gear. tp is number of teeth on pinion. Now let me start with the equation for velocity ratio. Equation for velocity ratio is nothing but dp. I made a mistake here. This is dg divided by dp, because diameter of the gear is going to be greater. So dg divided by dp. I'm going to divide by L. So dg divided by L, dp divided by L, and this gives me sine theta g divided by sine theta p. So first and foremost thing, when we are going to design the bevel gear, is to find what is the semicone angle. And semicone angle theta p and theta g can be found out based on the velocity ratio equation. So for an example, what they would do is they will give you angle. So between shafts is equal to say 70 degrees. What that means is theta p plus theta g is equal to 70 degrees. This is one equation. But to proceed with the design calculations, we should know the individual values of theta p and theta g. And one way to find this is use these two equations. So we have another equation, sine theta p is equal to say 70 minus sine theta g. Sorry, 70. Yeah, so sorry, I made a mistake here. So this is, so if I give you the velocity ratio is equal to sine theta g divided by sine theta p. So this is the second equation. So using, now you have two equations and you have two unknowns. So you can find out the values of theta p and theta g. Now the next part is important proportions. So what are the important proportions? So first is addendum, which is module. Second is dedendum, which is 1.2 modules. Third one is clearance, which is 0.2 times module. Fourth one is working depth, is 2m. The fifth one is thickness, is equal to 1.57 m. And if you want to, and the last but not least, this is super duper important. Remember, in the case of helical gear, we converted helical gear into an equivalent spur gear. The same thing with bevel gear. In the case of bevel gear, we are going to find out the equivalent number of teeth. So equivalent number of teeth on pinion are going to be number of teeth on pinion divided by cosine theta p, and equivalent teeth on gear will be number of teeth on gear divided by cosine theta g. Now there is something I need to talk about. So how do we determine these relationships? Like how do we convert? So I want you to just try to visualize a bevel gear. Bevel gear is actually a three-dimensional gear. It's not a planar gear, because you have something in X and Y plane and you have something extruding in the Z plane. So what you have is you don't have a planar gear, but you have a three-dimensional solid gear. So to convert a three-dimensional bevel gear into its equivalent two-dimensional spur gear, please try to understand, why do we say spur gear is planar? Because if you take a plane, you would see the spur gear fits in one plane. But if you look at the bevel gear, wherever you take slice, the dimension of that bevel gear, the dimension or what you see in that slice would be different. So in other words, bevel gear, you cannot approximate the bevel gear with just one slice. But if you take a slice of the spur gear, you can get all the principal dimensions. So what happens in the case of bevel gear, there is something called as Treadgold's approximation. So Treadgold's approximation is a geometric technique of mapping three-dimensional bevel gear into an equivalent two-dimensional spur gear. So I will write this down. So Treadgold's approximation. So what this Treadgold's approximation is? This Treadgold's approximation is a geometric technique or a geometric construction that will map this three-dimensional bevel gear into its equivalent two-dimensional spur gear. So these relations come from Treadgold's approximation. Now, some of you may ask me why this Treadgold's approximation is needed. So please try to understand that these gears are being designed for last 60, 70, 80, hundreds of years. At that time, we did not have sophisticated CAD tools. We did not have finite element methods. So what we had was just basic strength of material calculations. And those strength of material calculations are super restrictive because we assume plane structures remaining plane structures, deformation not exceeding beyond certain values. The deformation is restricted only in two dimensions. So we need some approximations, or we need some techniques to come up with some reasonable approximations that would be able, that would sustain the design loads. That's why all these Treadgold's approximations and other stuff that came into existence. But clearly, these approximations and these techniques that were proposed maybe 70, 80 years ago, they worked because those approximations, those empirical dimensions or rules of thumbs were tested again and again and verified in actual practice by lots of experimentation. So that's why the first step is always doing some back of the envelope calculations the way we are doing, getting some approximate dimensions, and then using sophisticated software tools to verify or to modify our calculations. So I tell you many a times, I see engineers just, if they ask you to design something, they directly jump onto SolidWorks and start designing something and run through the finite element analysis and say, hey, my design is safe. But think about it, like softwares are like garbage in, garbage out. So many a times the calculations or the designs that they have, they do not make sense at all. But still they say, yeah, this is what I've fed into the software and this is what came out. So please try to use something called as engineering sense. So please try to have some understanding of what the dimensions should look like before you get or before you obtain answer from the software. That will actually give you a lot more confidence in your design than just trusting the software blindly. So with that, and I would be honest with you, I have spent a lot of time designing lots and lots of elements, lots and lots of robots. And still now I go back to the same design principles before I jump on to SolidWorks or any other CAD software. Because once I have these basic dimensions, I kind of have an understanding of what would be the sizes I should be looking for, what should be the material I should be using. That would also give you tremendous insight into the bearings that you are going to choose, lubrication that you are going to choose, the weight that you are going to deal with, then what type of service factors that you might want to think about, and overall reliability of the system. So please don't jump directly onto the software. Try to do some hand calculations, basic calculations, to get an understanding of how your design would look like. And that will save you a lot of headache down the line. So design steps. So first design step is WT is equal to P divided by V times CS, where P is equal to power, V is equal to pitch line velocity, and CS is the service factor. And if service factor is not mentioned, you can assume the service factor is equal to 1. If the gear train is loaded heavily or it is continuously operated, you can assume the service factor anywhere between 1.2 to 1.3. Step 2, WT. Now we are going to use the beam strength equation, sigma naught multiplied by CV multiplied by B multiplied by pi multiplied by Y prime. What is Y prime? Y prime is the modified Lewis's form factor based on equivalent number of teeth. We use the same equation for helical gear, but there is a small change in the bevel gear. In bevel gear, we multiply with another non-dimensionless number, which is L minus B divided by L. And as you know, L is the cone distance, sigma naught is equal to static stress, CV is equal to velocity factor, then B is equal to face width. For bevel gear, the face width proportions are 12 times module to 20 times module. Y prime is Lewis's factor. L is the cone distance. And that is, so radius of pinion square plus radius of gear square. So this is just like a Pythagorean theorem. This can also be written as dp by 2 square plus dg by 2 square. Now CV is 3 divided by 3 plus V for regular gears, and CV is equal to 6 plus V for precision gears. Okay, next step is a determination of dynamic load. So dynamic load is given as WD. WD is equal to WT plus 21V B times C plus WT divided by 21V plus square root of B times C plus WT, where V is the pitch line velocity, B is the face width, and C is the factor that comes from the tooth error correction, and so on and so forth. And we are going to use the same tables that we used for the spur gear. Next step, WS is equal to sigma E times B times pi times M times Y prime multiplied by L minus B by L. And sigma E comes from the same table, which is 28.8. And the condition is static strength should be greater than dynamic load for gear to be safe. So this is the condition that must be satisfied. Next step, is we need to find out WW, which is always done for the pinion, which is the wear load, times B times Q times K. Small change to this equation. This is going to be cosine of theta P, where theta P is the semicone angle. Q is 2 EG. This is very important. These are the equivalent number of teeth divided by TEG plus TEP. And again, the condition is WW should be greater than WD. And the last part is shaft design. Now, please understand, shaft design is little bit complex because this is now a three-dimensional loading. So what I'm going to do is I'm going to show you how the gear structure looks. So shaft design. So in the shaft design, again, there are different ways the gears can be mounted. So let me give you an example. So here, say this one gear is sort of simply supported and the second gear is cantilever. Then the shaft design process for these two shafts is going to be slightly different because the maximum bending moment on the horizontal shaft will be different compared to the bending moment on the vertical shaft. So the total bending moment is going to be different, and clearly you will be designing two different shafts. But let's try to find out the loads. The loads are, you are going to have a normal load. So there will be a Wn. You are going to have a radial load, Wr, and then you would have a tangential load. And please understand, in this configuration, the tangential load is coming out of the board. So Wt coming out of paper. So this is a three-dimensional state of loading. So Wt is equal to torque divided by radius of gear, assuming we are designing the shaft for the gear. Then Wn is equal to Wt divided by cosine phi, and Wr is equal to Wn multiplied by sine phi, where phi is the pressure angle. Now, what are the steps? So I will just write these down. So Wt is a tangential load. Wn is a normal load, and Wr is the radial load. So with this, step number one, it find reactions. Step number two, find bending moment maximum. Step number three, find torque, which is torque square plus bending moment maximum square. And step four is using the equation tau is equal to TEQ divided by J multiplied by R. And we have been using exact same steps so far when we designed the spur gear or the helical gear. Now, let me quickly repeat the process, and then if there are no questions, I would go ahead and I will quickly work out a problem. So these are the major parameters for the gear: addendum, dedendum, clearance, working depth. In the case of helical gear, in the case of bevel gear, an important relation to think about is finding the equivalent number of teeth and then finding out the semicone angles. So these two equations will be used to find out the semicone angles. Next, first step is find out value of WT, then find out the module based on the beam strength equation. Then next step is finding out the dynamic load, the static load. The next step, static load needs to be greater than the dynamic load, and the wear load should be greater than the dynamic load. And at the end, the design concludes with shaft design. Many a times, if they ask you to construct a housing, so if they ask you to design the housing, the easiest way to design the housing is first draw the gear pair and then construct the housing around it so that the bearings that are supporting the shaft are housed in that housing. So if you want to construct a housing for this particular design, now understand, so I'm going to give you sort of a layout, how would the housing design would look. So housing design, the easiest housing that you can think about is something like this. As long as the bearings can be supported, as long as the gears can be enclosed, then you can deal with this housing. Or what you can do is, this housing can be something like this as well. And then you can actually design the dimensions of the bearing and then house the bearings and then see if the bearing needs preload, and then you need to add the seals, the covers, the gaskets, and make sure that the gearbox is contained with proper lubricant, so that would actually cool the gears, that will actually lubricate the gears, and that would increase the lifespan of the gears. Okay, any questions from in-person or online students? Yes.
What is the power transfer efficiency of bevel gears closest for use?
Yeah, the power transmission capacity is actually it's quite high, so more than 85%. So power transmission capacity of the bevel gear, the power transmission capacity of the gear train is quite high, except typically worm and worm wheel. In worm and worm wheel, the power transmission capacity is low. But other gears,
the helical, spur, and bevel are all about the same.
About the same. And nowadays, if you see, what they do is you can actually run the gears, the newer gears, they have special lubrication techniques. So if you go to the gear design, you can increase the efficiency of gear transmission by selecting the appropriate materials. Because what happens is, if you select, so let me ask you this question: what makes something efficient? Which means the losses should be low. What are the major losses that can happen in power transmission? The losses would be because of friction. So if you can reduce the friction by appropriately sizing the gear, appropriate material selection, appropriate lubrication, then clearly the efficiency of the gear train would increase. Structurally, worm and worm wheel is supposed to be the most inefficient means for power transmission. But that is not by the, the, the characteristic, it's by design. Because we don't want, so worm wheel, wherein in the case of bevel gears, power transmission is unidirectional. So if you rotate the pinion, the gear would be rotated. If you rotate the gear, pinion would be rotated. In worm wheel, power transmission is unidirectional. So you rotate the worm, wheel would rotate. But if you try to rotate the wheel, worm is not going to rotate. Whole thing will break, but it will not rotate. That is what you need in a hoisting mechanism. So you don't want things to fall down when the power is lost to the motor. So there are advantages, there are disadvantages. And now sometimes what they do is there are some experimental designs where they add circulating balls in the gear transmission that actually makes the efficiency even higher. But those are specialty and special purpose powertrains that are used.
But it doesn't change depending on the angle the bevel gears are set at. So 10 degrees and 90 degrees doesn't change anything really.
So it actually does. And you may not, and why I say that is because I have seen in practice. So here is what I have seen in practice. So when the gear, the bevel gears are 90 degrees, they last longer, the same material, than compared to the bevel gears which are at an angle. And my suspicion is it's because of the uneven loading, or because maybe some manufacturing defects that become predominant when you are cutting the gears which are at an angle. But strength wise, if you look at the equations for the power transmission, usually the angle is does not change the power transmission efficiency. But I have seen in practice that the bevel gears which are at angle. So how do you, so let me ask you this question. This is just from practical experience. How do you know that the gear train is efficient or inefficient? So if you see a gear train, it would be in a gearbox, right? What is, if I ask you, these are two gear trains, this is one gearbox, another gearbox. Can you tell me out of these two, which one is efficient? What would you do? The first thing what you should do is you should touch it. Once you touch it, you will see that one gear train, out of those two, the gear train which is vibrating is basically losing a lot more power. Sometimes when you touch it, you will notice one gear train is running hot and other gear train is running cool. So you can say maybe the hotter gear train is more inefficient because it's generating more heat. But it may so be because the other gear train has more area of dissipation or the lubricant is different. That's why the heat dissipation is better. So usually when you touch those gear trains, you will see the gear train that is vibrating or gear train that is not smooth is basically because of more friction or maybe because of unbalanced loading. So that is something that you can just by visualizing, or you can see it. And then that's why sometimes what they do is on these gear trains. So I don't know if you have seen the gear trains for the turbines. They are huge. If you look at the gear trains for the internal combustion engines, the diesel engines that are used for marine applications, they are huge. What they do is they have accelerometers strategically placed. And every time what they do is they are monitoring the vibration signature that is coming from that particular part of the gear train. So that before the gear train actually fails, they know something is wrong. So they can actually take preventative action, or they can go and do some preventive maintenance and so on and so forth. So once you go in industry, you would see that type of stuff. As a matter of fact, in your automotive power transmission, you have sensors that are embedded in automatic transmission. And as soon as there is an anomaly, the sensor would actually give a trigger to the ECU, and then your check engine light would turn on, and then you plug in your OBD2 scanner, you'll see the code and it will exactly tell you where the fault is. So, yeah. Okay, any other questions? If there are no questions, I'm gonna work out a problem. So power to be transmitted is 35 kilowatt. Drive RPM 1200. Compressor RPM 780 millimeters. 780. It's a 90-degree bevel. Pinion 30 number of teeth. Pressure angle 14.5. And this problem is slightly different. In this particular problem, value of sigma W, which is nothing but the product of sigma naught multiplied by CV, is given to us, which is 280 divided by 280 plus V, where V is in meters per minute. And Y equation is 0.124 minus 0.686 divided by equivalent number of teeth. B is equal to L by 4. Velocity ratio is 1200 divided by 780 is 1.53. TP is equal to 30. So TG is equal to velocity ratio multiplied by 30, which is 46.1. So I'm going to say 46. Please note, you cannot have fractional teeth. Okay. So tan of theta P is equal to 1 divided by VR, and that gives you theta P is equal to 33 degrees. Theta P plus theta G is equal to 90 degrees. So theta G is equal to 57 degrees. This is for pinion, and this is for gear. If you have calculators, please crunch in those numbers and tell me if my answers are correct. Online students, in-person students, if you have calculators, please cosine 33, 5.77. $46, y prime, and what we should do is ideally we should do sigma O times y prime for gear. We should do sigma O times y prime for pinion and find the weaker element. but since it's gear and pinion, same material, so pinion is weaker. So we are going to start with the design. Can someone quickly check my answers? Online students? Any comments? Online students, are my answers correct?
Yes,
So we are
you
going to
are
design
correct.
pinion. Yeah. So step number 1, WT is equal to P divided by V times service factor. Nothing special. So service factor will be assumed as 1. Velocity, pitch line velocity is pi times d times n by 60. So this is pi, and diameter is m times tp. Now it is super duper important, and I want you to make note of this. This is where the students make mistake. The equivalent number of teeth are only needed for module calculation. However, for all other practical purposes, diameter is equal to number of teeth multiplied by module. So you would use not equivalent number of teeth, but the actual number of teeth multiplied by 1200 divided by 60. CS is equal to 1. Power is 35, 10 to the power 3 multiplied by 1. So whatever answer you get, can someone tell me the value of VP? It will be in terms of module. So module is going to be floating around. So there will be module here and a number. So please work out that and tell me what that number is. So next step, WT is equal to sigma naught times y prime times b times pi times m times L minus b by L. Now here, I just want to give you something to think about. This is the actual process. So what you will do is, you will go to the table. For steel, you would find out the value of sigma naught. You know the value of y prime, and then you can substitute everything else and find out the module. But in this problem, the variation is, they have given us this equation for sigma W. So you have two choices, and there is no preferred choice. Both approaches are okay. So what you can do is, you can use this equation. So no, please note, this is sigma W. You can use this equation, sigma W is equal to 280 divided by 280 plus V in meters, meters per minute. So here, whatever equation you get, this guy, clearly, since your module is in millimeter, this will be in millimeters per second. So you would divide this quantity and substitute that in the equation over there. Please note, this must be in meters per minute. So you cannot add dollars to pesos. So it will be pi times D times N, which is 1000 200 divided by 1000. So this equation is going to become 280 divided by 280 plus pi times module multiplied by number of teeth times 1200 divided by 1000. You can substitute this equation here, or you can use the table and find the values. So I just went let me give you what values I get from the table. And both approaches are correct. And once you substitute this, which is 4 times b minus b by 4b, because b by L ratio, L by b is equal to 4. This is given. What happened? Okay. So L by D ratio is given. So here, substitute all that. And here we are going to get 18.6 divided by M, 140, 0.104. B is 12 times M, pi times M multiplied by 0.75. Solve this equation using trial and error. Module is 8 millimeter. Diameter of pinion is 30 times 8, which is 240 millimeters. And B is equal to 96 millimeters. Step number 2 is find the dynamic load. WD is equal to WT plus 21V BC plus WT divided by 21V square root of BC plus WT. And this equation is 2321 plus 21 multiplied by 15. B, I want you to take a look at the equation for B, which I got at 618, 96 plus 2321 divided by 21 times 15 plus square root of 618, 96 plus 2321. And WT is equal to P divided by V . 0.24 times 1200 divided by 60. WT is 2321 newtons. And then you can find out the value of WD. WD is, can someone check my answer? What is the value for WD? Next step is we have to find out the static load. WS sigma E B times pi times M times Y prime multiplied by L minus B by L. So you can, so sigma E 490 Newton per millimeter square, and you can actually substitute these values. You can select the appropriate BHN. So I used BHN is equal to 400 BHN. So you can substitute these values and I got 124 kilonewtons. Next step, WW is dP times B times Q times K. It's 240 times 96, 1.4, 0.88. Q is equal to 2 TEG divided by TEG plus TEP. So 2 times 84 divided by 36 plus 84. K value is equal to sigma ES square sine phi divided by 1.4, 1 divided by EP plus 1 divided by EG. Steel, so EP and EG is equal to 200 10 to the power 3 Newton per millimeter square. So you can substitute these values. So value of K is 0.88. So substitute these values and get, for design to be safe, WS should be greater than WD, WW should be greater than WD. Shaft design. And it's up to you what type of configuration you want. So I will just start with a very simple configuration. And this is totally up to you. We have shaft over here, bearing over here, bearing over here. I'm going to assume this distance to be 200 because this distance is 240. And I think this distance is 96. So I wanted to provide some clearance. And with that, WT is equal to 2321 newtons. Wn is equal to 2321 divided by cosine of pressure angle 14.5. Wr is equal to 2321 multiplied by sine 14.5. So the maximum bending moment in the, because of the tangential force is Wt multiplied by L divided by 4 because it's simply supported 2321 times 200 divided by 4. Wr L divided by 4, 581 times 200 divided by 4, 581. And then Bm total is going to be Bm T square, Bm R square. That gives you 119 Newton meter. Then T equivalent is equal to square root of T square plus Bm total square, which is square root of 278 square plus 119 square. That gives you 303 Newton meter. Tau is equal to T divided by J multiplied by R. Tau, we are going to use carbon steel. So 45 or 50. This 303 10 to the power 3 pi by 32 t to the power 4 times d by 2. And my d is equal to 55 millimeters. So this is how you would complete the bevel gear design. And I think your homework 5, right, asks you to design a bevel gear. Is that right?
Yes.
When is it due? Sometimes April 10th or something?
Or five.
Homework 5 is due tonight? Okay, so I would give you an extension on homework 5. Just can someone check what is in the homework 5? Is it bevel gear design?
No, voice five is good.
Oh, what is in homework 5?
Here's the first problem, but I'm not sure about the second problem.
I just want to make sure that you guys have enough time to work on the bevel gear. So please check quickly that I don't want to. Helical gear in homework 5. Quiz 5 is bevel gear. Thank you. And when is it due? Okay, 12th. Okay, so you have enough time to do bevel gear. So no changes in the due date unless there is university excuse. Thank you. All right, I'm going to stop here. And I will ask if anyone has any questions.